I would like to introduce you to the work I have completed this semester for my senior thesis in computer science. The project utilized haptic technology and the programmable Now robot to create some new ways to conduct post-stroke upper extremity rehabilitation. A stroke, or cerebral vascular accident, interrupts blood flow in the brain, which damages surrounding brain areas. The motor and sensory capabilities controlled by those damaged parts of the brain may in turn be affected by a stroke. Nearly 60% of stroke sufferers experience extremity dysfunction resulting in paralysis, muscle weakness, loss of range of motion, decreased reaction times, as well as numbness and decreased sensitivity. Upper extremity strokes affect the arms, shoulders, elbows, wrists, and hands and can produce both gross and discrete deficits. When these functions are compromised, day-to-day living becomes a major challenge. Fortunately, methods of rehabilitation exist to help patients with remediation and return of function for motor abilities and sensory awareness. Therapists have been rehabilitating stroke patients for decades, but the work is often repetitive and labor-intensive, therefore making it hard to sustain the motivation of participating patients. Robots can now be equipped with motor and sensory capabilities that are useful in expanding the post-stroke rehabilitation repertoire. My thesis applied haptic technology to rehabilitation. Haptics is an engineering field which explores touch interactions between a human user and simulation engine, or robot. My project involved programming and utilizing a Now robot to perform aspects of a post-stroke upper extremity therapy routine. The Now robot is a programmable 57 centimeter tall humanoid robot with tremendous movement capabilities due to its 25 different joints. It has a voice synthesizer, LED lights, 2 high-fidelity speakers, and microphones. It can identify verbal commands, detect motion, and recognize tactile stimulation of its hand, foot, chest, and head sensors. I programmed the Now robot to randomly produce a pose, which the patient matched by extending their arm and contacting the robotic hand. The patient touched the head again to set a new position. The patient could also touch the Now's foot sensors to return the robot to the ready position. The rehabilitation routine is conducted through all of these touches. Robots like the Now, unlike human therapists, can repeat movements ad infinitum with maintained preciseness. Since repetitive practice of movements helps with reorganizing cortical pathways following brain injury, the Now's capacity to keep generating random poses permits extended practice and optimizes recovery. It has also been shown that rehabilitation utilizing purposeful and familiar movements is better for neuroplasticity than rote exercise. In this routine, a few of the Now's poses imitated the high five gesture and modeled reaching as though for an object on a shelf. These are rewardingly familiar motions for stroke patients. Employing robotic and haptic systems to rehabilitation seems to motivate patients to practice, perhaps due to the excitement of interacting with a robot or the Now's verbal encouragement, which can be programmed. The Now has the potential to be an excellent adjunct to the rehabilitation therapy repertoire. My desire to learn more about haptics and challenging my programming and engineering skills yielded a project with utility in the work of rehabilitation therapy and so many other possible applications.